很多面，真的就比较没有后顾之忧。
有，我在想说，现在教务长在歌场，
对，又在歌场。
然后每天9点都要歌场。
我想说歌场的时候，我就可以那个停止一下，我就把那段剪掉。
对啊，因为我自己觉得，即便有麦克风直接收音，我看到那一段我都听不太到。
对啊，而且我已经有先调过，因为第一次的时候我就调过一次，第二次小朋友在跟我说又在调。
另外一个选择是我们开门不开窗。
哦，好啊。
窗户2层窗户玻璃关起来应该会好。我把门打开。
他的歌潮真的太猛了。
还有加高我的隐形管。这样好像好多了吧？
这样好多了。
对啊，
有可能。当然，命跟噪音还是命比较重要。James 那边 OK 了哈
？OK。
拍得到整体。
可以，就比较过去那边拍得到。
高斯这2个字看得到。
可以。
我这一台有自动对焦的功能，所以我在人在走的时候，它会是
对，大概对。
那我如果走到这边，后面就会看不清楚嘛。
啊，有的时候。
自动对焦能不能取消？
这好像是镜头的。
好像是软体里面，你
回去研究一下。
自动对焦是谁的功能？硬体有这个功能，但硬体自己不会做软体，所以应该是你的 YouTube 里面会有一个。我在 Skype 的时候 ，Skype 里面有一个可以关掉自动对焦。不过算了，差不多。开始了。Okay. Good morning. I hope you enjoyed your long weekend, long vacation by staying at home, not going to the southern part of Taiwan. A quick recap of what we covered last time. So Coulomb's law started from knowing the E field intensity distribution as a function of space for a point charge. So everything according to Coulomb's law is based on a single charge. If you have a single charge in space, it will set up a E field distribution that is inversely squared to your distance. Okay, so basically the charge divided by 4 pi epsilon 0, that's the vacuum permittivity, and then divided by the distance squared. And the direction is depending on the sign of your charge. So Coulomb, I forgot to record it. Okay. So Coulomb was able to calculate if you have continuous charge distribution based on the knowledge of a single charge. If you have a continuous distribution, but locally each point is only comprised of a single charge. So once you know the single charge E-field distribution, you can just sum them all up, right? So these are the three potential charge distributions: volume, surface, two-dimensional distribution, and line distribution, the one-dimensional distribution. So starting with the discrete charge, you have the charge value, and now you have distributions, you have charge densities, right? So one thing I have to note is the unit vector AR here is not limited to spherical coordinate, okay? This AR means the distance vector from your observation point to that differential charge segment, right? So this R is changing. This is not limited to spherical coordinate, right? Okay, so now we're going to look into one practical problem. Assume we have a uniformly distributed charge into a line geometry. We want to derive its resulting E-field intensity. How should we start? Now, based on the knowledge of Coulomb's law, we have a line distribution, so we have a line charge density. So in this case, the integration is only one-dimensional. It's just along the line, right? So dl prime. So again, you see differential length for different orthogonal coordinate system will be extremely important. So now we're going to invoke this equation. We're still using Coulomb's law, but now we have a geometry already specified. It's a line distribution. And the distribution, the charge density is uniform, meaning the charge density is a constant. It's not spatial. The first key issue is choose your preferred orthogonal coordinate system wisely, right? You have to choose a convenient coordinate system so that using this coordinate system, you can easily write down your equation: differential length, differential surface, differential value, right? So think about it. You have a line, and on this line, you have lots and lots of charges uniformly distributed. Which one of the three orthogonal coordinate systems should be most suitable for this particular case? If this line has certain radius, basically it looks like a tube or a cylinder. For that reason, for this particular problem, we want to use cylindrical coordinate. Okay, so R, phi, and z. So now you have to think back what I covered for cylindrical coordinate system, right? So we are going to invoke the Coulomb's law. So we have to know how to write down the unit vector for each differential charge segment, right? So let's first take care of this AR, unit vector. Along this line, I have an observation point, P, which is distanced by R, the radius in the cylindrical coordinate system. So for a given differential charge segment, dz prime, its z location is z prime, right? So this segment has its z value of z prime. Again, I'm using the primed system to denote the charge. I'm using the unprimed system to denote the observation point, right? Now, this R, this is the R, the position vector. It will change as your differential charge segment changes its Z prime value. So the first thing you have to find out is how to properly formulate this AR, right? So once you know this R position vector, you basically know AR. AR is just the unit vector. So this R is basically your uncapitalized R vector. That's a distance from the observation point to the center of your infinitely long line distribution. So this is a radius. Radius minus Z prime vector gives you R vector. Okay? So this R vector is your uncapitalized radius vector minus Z prime vector. Right? So once you know this R vector, you know its unit vector. You just divide it by its absolute value, its length. What about dl prime? dl prime is the differential length that you are going to integrate for this uniformly distributed line. So in this case, we can just integrate from negative z to positive z, from negative infinity all the way to positive infinity, assuming this line is super, super long, right? So in this case, since we have invoked cylindrical coordinate system, here dl prime is just dz prime. Okay, it's in the z direction with an amount of dz. Again, I'm using the prime system to denote I'm working on the charges. And here the r is the observation point, so it's not having the prime. Okay, so now that we know how to properly formulate this unit vector and this differential length, we can just write down for each differential segment of charge, for a very small length on this line, it will contribute its own E field intensity, right? So that's why I have a dE vector. So this is coming from a very small segment on the line. So this is what I invoked, right, using Coulomb's law. Now take a close look at this mathematical formula. You will have two contributions. Your E field intensity is a vector, so it will have many components, right? Up to 3 components. But up to now, we see we have the radial component, and we also have the Z component. So let's write it down for you. For each differential segment on the charged line, each segment will contribute 2 components. One is pointing in the radial direction, the other one is pointing in the Z direction. Both needs to be performed with a line integration. So at this point, this is the decisive point. It really depends on your knowledge and your understanding to the entire problem to be solved. Maybe one of your fellow classmates can finish the same problem in 1 minute, but you have to spend maybe 3 minutes. Why? You have to be careful. Now you have 2 contributions, but do you need to calculate both? What do I mean by that? Look closely. So now we're illustrating the E field intensity, the partial contribution from this small segment. right? So the R vector is pointing downwards with certain angle, but somehow at the observation point, I can divide it into the radial direction component and the z component. Right? So I do have two components. That's according to my anticipation. And truthfully revealed in my derivation, I have two components. This is the z component, and this is the r component. That's fine. But at this moment, think about it. Do you really need to perform the line integration for both components? For the z component, currently I have a differential segment having the positive z prime position. And that segment is giving me a z component pointing downwards. So here, I have assumed my charge distribution is having positive charges. Right? So all the fields are pointing away from the line. And therefore, when I have a positive z offset, that creates a downward E field intensity component in the z direction. But now the argument is, for every differential segment, well, on top, having the positive z prime value, I can find a corresponding differential segment at the bottom, right? Because in the end, I have to integrate all z prime positions. So I can find a corresponding, having some symmetry. So having a negative z prime value down here. And that differential segment is going to contribute a reversed z component, right? So for a differential segment down here, it will contribute the E field intensity in this direction. So I can divide it into a positive z component and still a positive r component. Therefore, you can see the z components are eventually going to be canceled out completely. But the r component will be accumulated for all the differential segments. Right? So this is the decisive point where you have to understand, do you anticipate non-zero field components? If there are non-zero components after the line integration, that's the component you have to perform the integration. So in this case, through our analysis, the z component will eventually vanish due to symmetry. On top, you have a downward z component. On the bottom, you have an equivalent amount pointing in the reverse direction. They cancel out. So the z components do not need to be calculated. You only need to evaluate the r component. Therefore, if you don't understand this, you have to perform both integrations. You spend 3 minutes. But your fellow classmate, who's very smart, who understands about the system due to symmetry, he only needs to calculate one line integration. So maybe 1.5 minutes. Okay? Makes sense, right? All right, so we only need to evaluate or calculate the r component, right? So we only have the r component. We perform the line integration. Now, limited by our mathematical skill, we don't have a way to directly integrate this type of integrants, okay? So now we rely on trigonometry. And that's what we learned in high school or junior high school. So we can convert this problem into trigonometry because we have a triangle here, right? So z prime, the z prime divided by r is tangent theta. All you have to do is define the angle. As we perform the line integration, we're changing the z prime value, and equivalently, we're changing this theta value. Okay, so theta is defined by this r position vector, the angle between this r and this uncapitalized radius r. Okay, so z prime is r, the radius, times tangent theta. You differentiate on both sides, so d theta prime. dz prime is r secant squared theta d theta. So now we replace that into here. And we also replace z prime with r tangent. So everything turns into a simple trigonometry integration. Okay, so this is z prime is r tangent theta, so that's the reason why I have tangent squared, because I have z prime squared. And if you still remember, 1 plus tangent squared is itself secant squared. Right? So this integration is very simple and straightforward. I'll go quicker because everything here is just mathematical derivations. So in the end, whenever we need to solve a problem in electromagnetics, the first important thing is to choose a good coordinate system for you to work with. If you choose a wrong coordinate system, you can still get the same answer, but you have a lot of processes. So here we chose symmetrical coordinate. It's easy, right? Easy and straightforward. And in the middle, whenever you have multiple E field components, like in this case we have 2, but maybe one of the component will be canceled out completely due to the symmetry of your geometry. You don't need to calculate it. That saves time. But at the same time, it relies on your basic understanding to the problem to be solved. And that's what I want to emphasize. I'm not here to teach you about mathematical derivation. I'm here to teach you the physical senses. You need to be able to judge which element, which component will be canceled out. That's really your understanding. Okay? All right, so this is a very simple illustration on how to use Coulomb's law. Coulomb's law, in my own personal opinion, is more tedious because it treats everything as the sum of single charges. So you have to do a lot of integrations. The next, a more powerful tool I'm going to introduce later is called Gauss's law. Right? It's easier, more friendly, user-friendly, and I will show you. Working on the same example, but using a different method, different approach, would save you a lot of time, right? So first thing first, the definition. This is nothing new. We talked about this equation already when we introduced the integration form of one of the 2 fundamental postulates. So this is your E field intensity distribution as a function of space. If I evaluate the E field intensity over a closed surface, this is what this means, right? This is coming from divergence. If I have outward flux of the E field intensity, I evaluate it over a closed surface, that would be equal to how much charge is being included within my surface, and then divided by the vacuum permittivity. So this is identical to the integration form of the fundamental postulate. Nothing more, but it's called Gauss's law. So Gauss was able to connect the differential form, and he invoked divergence theory to come up with this formulation. So this formula is coined under his name, right? So the physical interpretation, again, the total outward E field flux over any closed surface. You have to have a closed surface. That's the main point. The surface has to be closed. All right? So remember, this surface integration has a circle. You have to have a closed surface. And within this closed surface, you might have lots and lots of charges. Gauss does not really care about how these charges are distributed. He only cares about how much do you have. Okay? So if you have the flux over any closed surface in free space, remember we're talking about free space, and that E field intensity is determined by the total charge you have within this closed surface, and then divided by the constant, right? Okay, note here, this simple mathematical equation is extremely useful for you as a student to find out the E field intensity distribution. Let me show you one quick example. Extremely powerful tool. The first problem here, if we have a thin shell of charges, so let me draw it for you. I'm drawing a two-dimensional version, the cross-section. Eventually, the shell is three-dimensional. Okay, so I'm cutting the shell. I'm just showing you the cross-section. So if I have a lot of charges distributed along this metallic shell, so the shell is having a lot of charges. If you were to use Coulomb's law, you have to perform integrations, right, for each point. Because if I want to know the field, the E field distribution intensity at any given point inside the shell, without Gauss, you have to perform this type of integration, which is very difficult, extremely difficult. If you don't believe me, read example 3.2 in your textbook. You have to go over a lot of mathematical derivations. But Gauss is telling you, using his simple equation, right? He's telling you, well, if you want to know the E field intensity distribution, all you have to do is you form some kind of closed surface. And then you look for the charges encompassed by that closed surface. So if I want to know the E field intensity, any point inside the shell, all I have to do is, well, I can form, this is the origin, this is R, right? I can form a closed surface. This is a three-dimensional sphere inside the shell. The shell itself is three-dimensional, right? I'm only drawing the cross-section for you. And you know the surface area for that sphere is 4 pi r squared, which we derived, right? So now the problem is so simple. So this E times 4 pi r squared should be the total charge encompassed within it. But then the problem is, in here, all the charges are distributed on the shell. So no matter how you change the R, as long as your radius is smaller than the inner radius of the shell, you don't have any charge being encompassed. And therefore, inside the shell, you have no E field intensity. No charge. So inside the shell, no charge, no E. End of story. So if you have charge distribution outside, and you're somewhere sitting inside or standing inside of it, you don't have any E field intensity because you cannot encompass any charge, right? So Gauss's law, I mean, to me, is more like philosophy as compared to math. But the same problem, if you were to use Coulomb's law, you really have to go through all these three-dimensional integrations. But Gauss, like a philosopher, tells you if you cannot encompass charge, there's no field. Well, that's the case. Beautiful, simple, done. Okay. Now let's look at the problem we just analyzed using Coulomb's law. The same uniformly distributed charge line. The same problem. But when we use Coulomb's law, we went over some mathematical derivations. Okay, quite difficult. I mean, you have to remember trigonometry. But now we look at the same problem, but using Gauss's law. Okay, we still have this line with uniformly distributed rho L, the line charge distribution density. We still want to use cylindrical coordinate system. But when we use Gauss's law applies to the cases where you have good symmetries. In this case, you need to use a closed surface to encompass a portion of the line. So for example, I'm having this top surface is a circle, and the bottom circle, and then I need to use this tube, right? Total of 3 surfaces to form a closed surface. So I can encompass a portion, the length of L, on this line. And now you ask yourselves, do I need to evaluate all 3 field flux? So this one, this surface, second surface, and the bottom third surface. Do I need to do them? If you properly evaluate the total outward flux according to Gauss's law, you have to do it, right? Because this closed surface integration means you have to evaluate all the flux on all surfaces. So in this case, you have 3 parts that comprises your closed surface. Ideally, you also need to evaluate the flux flowing out in this top direction, the flux flowing out into the bottom direction and the flux flowing out in the radial direction, right? This radial direction. But then the question is, this tube is not giving you the whole answer. You need to have multiple tubes, right? Multiple tubes of length L. So if you have a second tube on top of it, this one, think of divergence, is flowing out, but the top tube has an adjacent identical surface pointing down. So basically the Z components will be canceled out. So in this case, when you invoke Gauss's law, to use it precisely and accurately is a test on your understanding to the symmetry. Just like in Coulomb's law, you need to be able to predict which component or components will be canceled out. So in this case, only the radial component remains. The Z components will be canceled out. So all you have to evaluate on this closed surface is just one, the radial surface. So how to properly formulate the differential surface, DSR in cylindrical coordinate. Radial direction, R defined, that's an arc length, DC, right? So basically, since we anticipate to have uniform E field intensity in the radial direction, all these areas have the same magnitude of E, so the integration is straightforward. ER times 2 pi r, that's your circumference, right? Times L, that's your surface area for that given radial direction. And that will be equal to the total charge encompassed. Rho L, a uniform charge density, times L, and then divided by the vacuum permittivity. And therefore, in just 3 lines, you arrive at the same result as we just analyzed using Coulomb's law. It's pretty impressive, right? The same result. Let's go back to the Coulomb's law, right? Same result, but you have multiple lines of mathematical equations. So this is showing you when you have a clear and deep understanding to the problem being analyzed, basically, try to use Gauss's law whenever possible, because Gauss's law can save you a lot of time and procedures. But again, when invoking Gauss's law, you have to have a very clear understanding to the underlying physics, especially pay attention to the geometries. Whenever you have quite symmetric geometries, invoke Gauss's law. No second thought. But if your geometry, your charge distribution is very asymmetric, stay away from Gauss's law, right? That's a truth to be told. All right, so we are able to arrive at the same result for a uniformly distributed line charge using Gauss's law, quick and easy, very straightforward. What about, let's go to a plane charge. Okay, so now we have a uniformly distributed charge plane. Under Gauss's law, we still need to use a closed surface to encompass a part of this charged plane, right? So the easiest one is to form a box, right? So a box is comprised of 6 surfaces, right? 6 surfaces. Now you have to think, Well, to properly formulate or evaluate using Gauss's law, you have a box. Ideally, you need to evaluate all the outward flux over the 6 surfaces. But in reality, do you really need to calculate 6 times? I mean, if you do the calculations over the 6 surfaces, you're not saving a lot of time as compared to using Coulomb's law. So the magic here is we can make the height of this box extremely short so that these 4 side surfaces have negligible surface areas. Okay? If you make this height extremely short, basically, they're not there. So you only have to evaluate 2 surfaces. The top surface, you have flux going out. For the bottom surface, you have flux going down. Remember, flux are defined flowing out. Okay? So for the top surface, your surface direction is pointing up, going out. But for the bottom surface, going out means you have to reverse the sign of your surface normal, going down. Right? So let me draw it for you. So again, I'm showing you the side view. So if we have some charge distribution, right? Assuming positive charge, we have a box, right? This is a cross section of the box. So for the top, I'm flowing out. For the bottom, flowing out means I need to reverse the sign, right? This is flowing out. Okay. So the charges, positive charge, emit field lines, right? In a radiant way, always away from the positive charge. So for the bottom surface, you need to change the surface normal to the negative direction. All right, so above it, you have E field lines going in the positive Z direction. Accordingly, your ds, now we're working in Cartesian coordinates. So Z, positive Z with an area of A. For the bottom surface, you know that the E field lines are pointing in the negative Z direction. But at the same time, your surface normal is also in the Z direction, negative Z direction, right? To account for outgoing flux. So you add them together, Gauss's law, in this case, only has 2 surface contributions. They are same in magnitude, so 2 times EZ times A, right? Now we finished the closed surface integration. All we need to do is calculate how much charge is being encompassed in that box. And that is rho s, which is the constant, multiplied by A divided by vacuum permittivity. Simple and straightforward. So the E field intensity, whenever you have a planar uniform charge distribution, above it, you have fields pointing in the positive Z direction with a magnitude of rho s divided by 2 epsilon 0. But when you're below it, the same magnitude, but only with a change of direction. Right? Now, the trick is, for most students, you forget about the bottom surface. I don't know why, but throughout the years, a lot of students just assume there will be only flux going out on the top. I don't know why. But remember, this Gauss's law tells you you have to evaluate the net flux for a closed surface. So everywhere you have to evaluate it. Okay, so a lot of students miss this factor of 2 because they only evaluate the top surface. Then you're wrong. And some students, after finishing doing a correct evaluation, reverse the sign. Okay. So remember, to keep your answers complete, you have to remember E field intensity is a vector. So the directions will change according to your observation point. So a better way and easier way to express this is the E field intensity due to its planar uniform charge distribution is z direction, but the sign of z. When your z is positive, sign of z gives you a positive 1. When z is negative, this sign of z gives you a negative. Okay? So writing in this way, usually you don't screw up, right? You have less chance of being wrong. You just add the sign of z. So when you're above the plane, you have positive z pointing field. When you're below the plane, you have negative pointing E field, right? So time is perfectly controlled. I still have 6 minutes. So before I go to the next slide, are there questions from the students? Any question from the students? James? No? Any question up to now? So let me re-emphasize again. So I have this blackboard design. To properly evaluate E field intensity spatial distribution, I have offered you 2 different approaches. One is using Coulomb's law. The second one is using Gauss's law. Right? The difference lies in Coulomb initially invoked Gauss's law so that he was able to formulate the E field distribution for a point charge. So his idea was, if I know the E field intensity distribution of a single charge, which is this, right? Inversely proportional to the radius, the distance squared, then whatever charge distribution, discrete or uniform, doesn't matter. Everything is being assembled by single point charges. So he relied on the single charge formulation and then performed the integration. Volume integration, surface integration, line integration doesn't matter. He embraced this point charge distribution. Right? On the other hand, Gauss sticks to this fundamental postulate. He's telling you, well, for any given problem, well, you just form a closed surface and you perform the integration, then the field distribution is determined by how much charge is being encompassed within that artificial closed surface. So this is a more generic approach. So this is suitable for very nice symmetry. When your system is having good symmetry, this is the proper way to go. Straightforward, quick, and precise, and easy. Coulomb's, when your charge distribution is weird, asymmetric, try to invoke Coulomb's. Right? So that's the difference between the 2. They work equally well, giving you the same result, ideally, if you don't screw up. But the pace, the time required, are very different, as I showed you. All right? To conclude for the day, I want to show you something amazing. Okay? This is really practical. Don't say that class is here in university are impractical. So to summarize, if we have a point charge would give you a radiant E-field intensity distribution, and that is inversely proportional to the square of your observation distance, right? So this is like a bulb. You don't see this bulb anymore. So this bulb would decay as you walk away from it, right? So let me draw it for you. Distance, E, strength. So this is a point. And then somehow through our derivation, we also analyze when the charge distribution is made into a line. Your result is the E field intensity is inversely proportional to the distance, 1 over r. What does that mean? Square. So this is a line. Okay. So whenever you somehow form the charges into a line distribution, the fields does not decay so fast. Okay? And the magical thing is, well, every one of you are using your monitors, liquid crystal monitors, laptops. It's more like planar, right? So whenever you have charge distributions formed in a planar way, the significance is the field strength, the magnitude is a constant. It's a constant for a planar. Right? So take a look around you. Look around you for all the lightings. In the ancient past, people relied on a single bulb. So it's very dim when you walk away from it. But later now, can you take a snapshot at our lamp? 拍一下这个灯. Yeah. This is very important, right? So look at the lighting structure that we have. Although we have light lamps now formed in a linear line structure, but somehow we have multiple lines and their reflectors, right? So the result is like a planar lighting. Why? Exactly due to this derivation. Whenever your lighting source or your charges are distributed in a planar way, you can enjoy the benefit of the same lighting amplitude, no matter how far you're away from it, due to this fact. Right? Your laptop has a backlit module mimicking a planar light structure. Why? You don't want the light intensity to decay as you walk away from it. Now try it. Move your eyes into your monitor or away from the monitor. Does the intensity change? It does not, because it is planar-like. Okay? So I'm trying to connect the findings over the past 2 classes, and I summarize it here for you, and I'm trying to link that to daily life analogies for our lighting system. If you want to have very uniformly lighting system that does not decay with distance, like in a classroom, you want to have multiple light bulbs, lamps in line geometry, or multiple of them, and you use reflectors, and you have a planar light source. All right, so that concludes for today. Thank you for your attention.